already know that a differential equation can serve as a kind of recursive mathematical model involving some quantity u and its various derivatives, among other things. You may not yet appreciate that it's often more convenient or even more informative to express a recursive mathematical model in a non-recursive way. The objective of this video is to show you how to move from a recursive model, stated as a differential equation, to a non-recursive one. In other words, the goal of the video is to show you how to solve a differential equation. For now, we focus on solving first-order linear differential equations only. We can express a first-order linear differential equation in the following way. Here, u of t is our unknown function, the thing we're trying to solve for. By contrast, p of t and q of t are functions that are given. We will assume that both p and q are continuous in t. To solve this equation, we first define a new function, v of t, as e raised to some power. For our definition, the power we will want is the antiderivative of p. Actually, it's any antiderivative of p that suits us. Returning to the differential equation, we multiply through by the new function v of t. This might seem like an odd thing to do, but it helps tremendously. To see why, consider v prime of t. We can compute this derivative by applying the chain rule to get p of t times e raised to that antiderivative power. Have a closer look at that. It's simply p of t times v of t. Now, cast your eye back to the differential equation. You can see that we have a p of t times v of t stuck in there too. So, our rough work on the right tells us that we can put v prime of t in place of that product to get this. What we have on the left-hand side of the differential equation is exactly what we would have obtained had we applied the product rule to differentiate v of t times u of t. This means that we can write the given differential equation in a very compact way. Besides looking quite elegant, this form of the equation points us toward a solution. Remember, we're trying to solve for the unknown function u of t. We can work toward isolating u of t if we now integrate both sides of the differential equation with respect to t. Doing this leaves us with v of t times u of t on the left, because integration undoes differentiation. It also leaves us with an integral on the right, but because that integral involves only known functions, we should, with any luck, be able to evaluate it. When we do evaluate the integral on the right, we must include the constant of integration. Once that's done, we need only divide both sides of the equation by v of t to obtain a formula for u of t. To be clear, this formula actually represents a family of functions whose members satisfy the differential equation. Now that we have derived our formula, let's turn our attention toward applying it with a specific example. Consider this differential equation. We can see that it's first order, and we recognize that it's linear. So we can solve it by applying our formula. Before we apply the formula, we should collect all terms in u and its derivatives on the left. Doing so allows us to see that, for this problem, p of t is equal to -1 and q of t is equal to e raised to the power t. In this example, both p of t and q of t are continuous functions of t. That's good news because it's exactly what we assumed when we derived our formula a few moments ago. In general, though, this won't always be the case. Sometimes p of t or q of t or both will suffer discontinuities. The assigned reading shows you how to cope with discontinuities, and the exercises will give you some practice dealing with discontinuous p of t and q of t. Returning to the task at hand, we can determine that v of t for this problem is e raised to the power -t. Notice that we've not chosen the most general antiderivative of -1 when defining v of t. Instead, we've simply chosen one that suits us, namely -t. We now have all the pieces we need to plug into our formula. We have u of t is equal to 1 over e to the negative t, all multiplied by the integral of e to the negative t times e to the t, plus c. We add the plus c here to remind us that we're interested in identifying a family of functions that solves the differential equation. Simplifying the previous line, we can write e to the t rather than 1 over e to the negative t. We can also write the integral of 1 in place of the integral of the product of exponentials. After evaluating the integral, we have our family. U of t is equal to e to the power t, all multiplied by t plus the constant c. Since we now have an explicit mathematical statement involving u and t, we can use a plot to express the relationship between these two quantities. Using high school math, you can see that any curve that expresses a relationship between u and t will have a root at t equals negative c. So, if c is equal to negative 1, for example, the root would occur at t is equal to positive 1. Using elementary calculus, you can also see that any curve that captures the connection between u and t will have a minimum at t is equal to negative c plus 1. If c happens to be negative 1, then the minimum would occur at t is equal to 0. We can also see that u increases without bound as t becomes large in the positive direction. Using L'Hopital's rule, we see that u tends to 0 as t becomes large in the negative direction. The same ideas also help us plot other members of the family of functions. When c is equal to negative 2, u has a root at t is equal to 2, a minimum at t is equal to 1, and the curve looks something like this. When c is equal to 0, u would have a root at t is equal to 0, and a minimum at t is equal to negative 1. The curve for this member of the family would look like this. We don't need to plot u versus t in order to find the particular member of the family that interests us. Suppose, for example, we were interested in finding the member of the family of functions that satisfies not only the differential equation we've been working with, but also takes a value of 2 when t is equal to negative 1. In other words, suppose we're interested in the member of the family that passes through the point negative 1, 2. To find the correct c, we recall that the family of functions satisfying the differential equation is this. We then put two pieces of information together. On one hand, u at negative 1 must equal 2, but on the other hand, it equals e to the negative 1 times negative 1 plus c. Solving for c, we find that the constant must equal 2 times e plus 1. And so, this is the member of the family of functions we were looking for. To recap, in this video we derived a formula that describes a family of functions. Each member of that family satisfied a first-order linear differential equation. You should be able to reproduce the derivation of the formula if asked to do so on a test or exam. We also used the formula to solve a particular example. Of course, you should be able to do this too. That is to say, you should be able to apply the formula to solve problems involving first-order linear differential equations, again, on a test or exam. Please remember, this video is just the beginning. Be sure to read the course notes and try the practice problems. Also, be engaged, ask questions, challenge yourself and your classmates, and you'll be surprised how much fun math can be.